And also, before I begin, I want to thank a load of people that I collaborated with to do this work. All right. So the setting that I am thinking about the most is going through some AI system. And that AI system is producing an output like a decision, that it's a recommendation that someone takes. But the clinician, I work mostly on health applications, also has available to them some other information. For example, this patient is, master of all 4 elements, and there's just no ICD-9 code in the system currently, that captures that. So you might need to adjust your treatment strategy based off of things that you know about. Right? So really the right question shouldn't be, we shouldn't be creating AIs that output decisions most of the time. Sometimes we're upskilling people and we do need to just have people follow directions, and having people think, should I follow the decision? But maybe the right way to be thinking about this okay. Should be how to make the decision, right? That the agent should really be sending some type of information, and then the human combines these ideally to make a better choice than they could have without the AI system or with the AI system. And when I think about interpretability, I really want to emphasize that there has to be something that can't be fully formalized, right? Like there has to be a reason why we need the human in the loop. When so my undergrad was an aerospace, like a key example they would give about like cool company stuff was at the time was like next generation TCAS of 2 planes are coming at each other, one plane needs dynamics. We do not need a human in the loop. And in fact, when humans are in the loop for some of those decisions, things have gone badly. Right, so that's an example of a system that can be fully formalized. It can be fully mathematized, and we can just solve it. But there's many other situations, especially when you are interacting with people, that cannot be fully formalized. And so that's really the regime that we're living in, just to make it clear. I'm not saying that you need interpretability always, or you never need it. So sometimes, right? There's certain cases that require it. So what I'd like to do is I want to start out by just presenting a little bit about my philosophy on how interpretable machine learning works. And then we will dive into some opportunities for generalization in that space. So here's my high level picture. So the usual machine learning system is that there's some data, we make a model, we get an output. There was some score that was used to produce the training of the model, and we get some score for the quality of the model. In the interpretable machine learning setting, oh dear, okay, we've got this stuff going on here. In the interpretable machine learning setting, we have some larger tasks that we're trying to solve, right? Like we're trying to treat this patient's disease. And the model might not have been trained with all the data that goes into, as I mentioned, trying to treat that patient's disease. So there's some additional data that's available. And the human is a decision maker. So the human gets the additional data. They might also have the data that went into the model, though no one is maybe going to have time to go through all of those health records. They're going to get some explanation from the model, and they're going to get the output from the model. And based off of all of these things, we hope that they make a good decision that helps us in real life, not some proxy function that was used to train just the model. So that's the setting that we're in. The data, the model, additional data. We're trying to make a good decision. So the reason why this endeavor is difficult is that we have many choices of what to send in terms of our explanations. And different tasks are going to need different information or different choices of explanations. And to really get the evaluation bit over here, the real score requires some doing this in real life. Because if it didn't, then it would be a fully formalizable problem and there would have been no point, right? Like we didn't need this whole thing in the first place. So that's what makes it difficult. And what I'm going to propose, and first of all, when I say there's lots of explanations, there truly lots of it. Like if you just Google for the number of like explainability methods, interpretable ML methods, prototypes, inherently interpretable functions, which features are important, and depending on which method you choose, it'll highlight different parts of the image. Same model, right? Just different explanation methods are pointing out different parts of these images, right? So there are just so many choices, right? So when I say over here that, many choices of explanations, we really are in a tough spot if we want to be able to do this, because again, each evaluation requires a user study, and that's expensive, right? So that's where we are with the many choices of explanations. What can we do about that? So what I want to present today is a conjecture and some work that we've done towards that conjecture of how we can solve this problem more. And the idea is that, okay, let's zoom in on a particular part over here. We have a task. We had the explanation. And then let's try to, see if we can create an abstraction here. That, what are the properties of the task? So maybe all the times that you have to do a task quickly under time pressure are similar in the sense that you have limited time to think. You can't spend a lot of time with the explanation. It can't be too big. So something about the task tells us something about what we need from the explanation. It cannot be too large. And then we can ask the explanation, well, do you satisfy those requirements, right? What are the content? Does the content of the explanation contain what it needs to contain? Is the delivery of the explanation such that the person can actually use it? So this is the conjecture that instead of thinking about specific explanation methods and specific tasks, maybe we need to be thinking about properties of tasks and properties of methods and putting those together. And
I think we should just. Why do we have Zoom if the speaker?
I know. This is ridiculous.
Okay. All right. So let me try to formalize or, at least conceptualize a little bit to what I mean when I say properties, right? So let's suppose that this is your function over here. Yeah. And I'm trying to explain this one particular point. And unfortunately, we got this thing across the bottom with there's X star over here. Yeah. And that's what we're trying to explain. Well, what's happening to that function at this point over here? Well, if we wanted like a highly faithful description of what that function's doing, maybe we would say, oh, the function's kind of going down, right? At this particular location. If we wanted something that was robust in the sense that it would apply across many points, we might say, oh, but in general, the function is actually going up, right? It's a very different answer. And if we're like, 2 parameters, I just cannot deal, then maybe you need a compact explanation that just gives you a single number, right? That it's a constant. So those are different examples of properties, like how small it is, whether it applies to nearby data points, whether it really precisely describes what happens at your particular data point. These are content of the explanation. That's going to be a focus of my presentation today, but at the very end, I will also talk about things about the delivery. Like, when do you present the information? Do you force someone to come up to their conclusion first and then say, but have you thought about it? Do you provide a recommendation at all, or just say, here's some useful information that might assist you in treating this patient, and many other options here, but just really emphasizing. I think one element of like humility that I have learned working in the human AI space is just the level of interesting mechanisms that people in the HCI community have come up with in terms of finding ways to deliver information effectively. All right, so but going back to this content stuff, I made it kind of look kind of simple, right? 1, 2, 3. And in fact, a lot of people have come up with a lot of mathematical formulations of properties. And recently, this is a little bit of a shame. We're cutting off the people's names. But recently, we just put up a post on Archive that goes through and categorizes a very large number of these mathematical formulations. So if you're interested in not having to dig through loads of them, but find them all in one place, we have the place for you. And in terms of open questions, okay. That I said I'd be highlighting throughout the course of the talk. People have been coming up with loads and loads of metrics or these properties. There are surely redundancies between all of these. Do we need this many scores? I don't think so. What are the formalizations that we actually need? So in terms of math problems that are kind of open problems in the interpretability space, I think one is just the condensing the number of properties that have been proposed and under what circumstances, because I drew that one function where the answers were different, just as an illustration. For many functions, it might not really matter. And so that's also, some really interesting open questions about, are the properties that we have, where every paper produces, that we want to measure it this way, right? What is the right way to do these sorts of measures? All right. But let's suppose that we buy this general idea, right? The grand plan toward generalization is that we're gonna take tasks and we're gonna link them to the properties that they need. And then once we know the properties that they need, we can make the explanation match the required problem, right? So let's suppose that that's gonna be our way forward. I'm gonna present some very early work. When I was like, I wanna present something new. So all of this stuff is in submission as of 8 a.m. this morning to AI stats or earlier deadlines. But it just share it, being transparent that because this is like kind of work just happening, it's still a bit, it's a bit rougher than stuff that we would have maybe that would maybe present that, it's been years long enough. But anyway, let's try to link task to explanation property. So the first question you might ask is, do different tasks need different properties? So a couple years ago, we did a survey of experts and we asked them, what properties are needed for capability assessment, decision support, all these sort of things. And and you don't need to read them all, but they highlighted different things. So that was cool to hear. We want to dig in a little bit deeper. So what we did much more recently is that we created a simulation of of how a person might make decisions. So let's give a memory limitation. Let's give a computational limitation and make a proxy person, basically, a very transparent proxy person, to identify when properties will matter. So we considered 3 different tasks, like identifying a forbidden feature, like are you using race inappropriately in a decision, being able to simulate a counterfactual, like what if something changed about this input, would the output change? And forward simulation, just being able to say that, what is my prediction of what the model is going to do based off of the explanation. We considered people that were unlimited in terms of their capacity for computation and people who were limited in ways that kind of seem sensible. And we ran a couple of different functions and tried a couple of different explanation properties: faithful explanations, sparse explanations, robust explanations, sparse and robust explanations. And what we noticed that in some cases, like over here, it really doesn't matter, right? The form of the explanation, like every case people can do well. Certain cases are just hard and no one's gonna do well if you have a limited think budget. For this particular task, the form of the explanation and this particular annoying function that you have to explain, you just can't do well. But we could identify situations where it looks like different explanations are needed for different types of tasks, right? So now we have this in silico. We do the sim to real, right? Because you are not the same thing as like a decision tree with a particular memory model. So we set up a user study, and this is just to make it concrete in terms of what we actually, what it looked like for the user study. So the user is told that there's some measurements that have been taken. The zoom is hiding. There we go. Is hiding the fact that there's a measurement that changes, one measurement that changes. You're asked, based off of this information, does the risk score go up and down? And you're told some additional information about the function in the form of an expert tells you that here's how the function behaves. And we found that people this is done on Prolific, people responded to this better than if we said like an AI tells you. So we call it an expert. But this is a sort of study that we did. And what we found, these are 3 scenarios that we tested, where in blue is like our prediction from the simulation study. In orange are the human results. The top row over here has to do, it shows only the top performing people on the task, the top 50%. And the bottom row shows all users. And what we find is that the top row actually matches quite well in terms of performance. And the bottom row, especially on these tasks, not so much. And I think this is interesting, again, in terms of open questions. So first of all, what's the cool thing? Like we did the sim to real thing to make it more efficient. So we didn't have to run loads and loads of user studies, but we did demonstrate that different explanation properties are useful for different tasks. Again, sped up with the sim to real framework. And there's an interesting open question of like how to continue to apply this type of sim to real framework for more complicated environments, creating more settings so we can try to, again, accelerate this science of people, right? Of like, what do people need under what sort of circumstances? Because that's the first half, right? If we need to figure out what they need in terms of properties, and then we can make the explanations that. So that's like the first half, again, of this endeavor. We needed to, because if people didn't need different explanations, what's the point of doing anything else, right? But now we've demonstrated that people do benefit from having different explanations depending on the task. Okay, and also I'm gonna go through this. I'm not gonna spend time on this due to the interest of time, but we did also check qualitatively, like, were they using the explanations in a way that was sensible? And we found when you get a sensible explanation, people were using, sensible reasoning processes, whereas if you gave them an explanation that really could not help them with the task, did not have enough information, then they were kind of faffing around and they couldn't figure out what to do. Okay, so what I've done is I've talked about some really initial work on linking tasks to explanation properties. And then the next part is how to optimize explanations to get the desired properties that they need, right? If people need something that's small, if people need something that's faithful to do their task, how can we make sure that we deliver on that? And remember, there was like that whole zoo, right? That was just a tiny subset of pictures of methods out there, right? And what do we do when we need to provide the right explanation in a particular situation? So this is, again, like a mental shift or a philosophy shift. But what I noticed is that current explanation methods tend to be defined by some very reasonable forward computation. So we say that, oh, the explanation is going to be the derivative of the function, right? Because the derivative tells us kind of how the function is changing at a local point. Oh, the explanation is going to be a derivative of an interior node inside the network, because that'll tell us how the node affects the rest of the network. So there are all sorts of, difference with some baseline point. And so it's defined in a way that's very reasonable. Very smart people have come up with this forward computation, but it's still kind of heuristic, right? It's kind of like, this seems like a reasonable thing to do, right? A reasonable smart person has come up with this idea. And even when there's connections to properties, it might not be such that you can tune the properties easily and say that, but I want it to be more faithful. I need it to be more compact, whatever you need. And so the question that I want to pose is that perhaps we should be defining explanations more transparently, right? We need to explain our explanations by what properties they satisfy and actually optimize them. Produce explanations are an object that are designed to spec, right? We create the spec, the properties that they need, and then the explanation is just the optimization to that particular specification. So let me give you again a flavor of what that might look like. So let's suppose that you decide to define fidelity, robustness. I'm going to add smoothness, because let's say you have some sort of pixel-based thing and you want two pixels that are near to each other to have similar explanations as your properties. And I'm going to start in the transductive setting. So we're given our set of explanations, the points that we need to explain in advance, that we're going to need explanations for this batch of endpoints. And for that batch of endpoints, for each of those points, let's suppose we want the explanation to be similar to some ground truth, like the gradient. It doesn't have to be the gradient, but this is like our fidelity loss, that we want it to be close to something local about the function. But we also want the explanations to be robust. We don't want them to vary too much from one point to a nearby point defined by some similarity. And let's say smoothness says that the explanation in one dimension needs to look like the explanation in another dimension if the dimensions are close to each other, right? So we define these sorts of losses. And if we define them all quadratically, by the way, in the transductive setting, we can do other sorts of things with quadratic programs and constraints and such like this, but I'm going to stick with this basic quadratic formulation for now. We can get something that looks pretty nice, right? Like you could have solved this in high school. Yeah, okay, right? Except for this L1 loss that we have to do a little bit more work for, but not much, right? College, right? That one you could do it when you got to college. So you get this very nice looking loss function that we can now optimize. And the point is that even this really simple thing gives us explanations that provide a Pareto frontier that is better than kind of the existing forward computation methods. So in red are examples across different functions of our approach. And so here is fidelity and robustness, like perfect would be at 0, 0, but of course you can't reach that. So you're moving out of space. This are two popular approaches, Lime and SmoothGrad, and they just kind of, sometimes they even go in the wrong direction. Sometimes they just kind of sit around at one point as you vary their hyperparameters. We also did SHAP, but SHAP did so poorly that we couldn't put it on the graph, but we have it. I could show you other graphs, but it's kind of out here. And so you couldn't see this very well. And this is interesting, right? This is interesting because these are go-to methods that are used. And what we're demonstrating is that there's just very simple ways of doing certain types of optimization that can get you something that lets you sweep out whatever optimal you want based off these trade-offs with precision, right? I can tell you exactly what I'm giving you, whereas these methods don't tell you what they're giving. All right, so this case over here involved working with the transductive setting, super simple, right? Now, let's suppose that we go to a more realistic setting, right? I don't give you the set of n data points that need to be explained in advance, and it's just a one-step problem. You come to me one at a time and be like, this data point over here, can you tell me what's going on? A little more. New patient comes in over here, like, can you tell me what's going on, right? So what happens in this setting is that those summations become integrals. So we have now a fidelity type loss, but now that fidelity type loss needs to apply over the entire data set. Our explanation becomes an explanation function, right? Because in the transductive setting, I just needed to output n different explanations, right? But now I need an explanation function that's going to output the explanation for any query point that you give me. So I need that function to be have high fidelity. I need that function to have desired robustness. I need that function to give me the desired smoothness. These two are maybe not so bad because they just depend on the single data point x. But this one is kind of annoying because it involves x and nearby data points. And in particular, let's imagine the following picture. So here's a function over here in black. And then in green, I'm showing the gradients of the function. So in terms of like, let's again assume that gradient matching is like the faithful thing to do. It doesn't have to be that there's other notions of fidelity, but that's the picture for now, right? So in green are the gradients of the function at 3 points. And let's say I'm interested in explaining x star, right? And I have to choose this gray line to be the solution to this thing over here. So if I'm choosing this gray line to be that solution, well, the fidelity term says make sure these two are similar to each other, right? The fidelity term says make sure that the gray line is similar to the green line. And the robustness term, let's say that these two are close to each other and these two are close to each other, says that this explanation needs to look like this explanation because I want it to be robust, right? I don't want the explanation to change too much across different inputs. But when I am trying to find this optimization over here, this one has another constraint, right? X prime has another buddy on the other side, x double prime, that has a gradient and has some explanation. And x prime really wants their explanation to be similar to both, right? So this is how you end up with a situation where when you're trying to solve for the explanation at x star, you can end up coupled to the explanation at x double prime, right? Does that make sense? Because existing methods, what they tend to do when they try to make things smooth is that they try to make E of x star similar to gradient of f x prime, right? But that's not the robustness target, right? That's not the smoothness target. What we care about is that we want the gray lines to be close to each other, not that this gray line is close to this green line. So that is what makes this hard, in terms of an optimization problem. Of course, if you're looking at this, and like I come from like the world of like Bayesian non-parametrics and GPs, you're like, oh, there's an observation and a smoothness condition. Like, I know how to deal with this. Or at least I know a way to deal with this, right? Like, this looks like a likelihood term, perhaps, because there's this unknown function E. And for that unknown function E, there's some things that, we want the function to look like an observation model. And then there's some smoothness stuff going on. And what we show is that the solution to this, under certain limits, corresponds to the mean of a specific Gaussian process. So this is the part where I show a little bit of math to show that there is math still to be done, even though data is maybe ruling most of the world these days. All right, so here we go. Suppose we have, now I'm going to say suppose, right? Suppose we have a Gaussian process with some mean and covariance function. That's going to be our explanation function. And we don't know what the mean is. So we don't know what the mean explanation value is. We don't care. So we're going to put a prior, because we're good Bayesians. We put a prior over the mean, which we don't know what it is. And we're going to treat the outcome, the gradient, as the observation of the Gaussian process. So this part over here is going to give us this thing over here. That's the likelihood term. And then because we don't know what the mean is, we integrate it out again because we're being good Bayesians, and we get a new prior on the Gaussian process and its covariance. And if we happen to substitute in a really specific covariance function, over here, we're going to assume that we really know nothing about this, so we're going to let the variance of the unknown mean go to infinity, so this term is going to disappear. And then if we substitute, I don't expect everyone to follow the math, but just giving a flavor of how we go about doing this. If we substitute a really specific covariance function in, then we recover something that looks very much like our original optimization problem, but now with specific notions of sim. So like before, I just had similarity over robustness and similarity for smoothness. And now I'm defining it in a really specific way. Why did I bother, right? So why bother doing all of this stuff to say that, hey, that original optimization that I had for interpretability, if we do this Gaussian process song and dance, can be written down, in a very similar form. Well, the good news is that we know how to work with Gaussian processes. We know a lot about how to approximate them. We know a lot about how to do inference in them. We know a lot about how to choose core sets to do inference really efficiently. So the original optimization problem, if you gave that to me, I'd be like, I don't know, how to exactly solve this problem. But if you tell me that, that we're trying to approximate this mean function of a Gaussian process efficiently with some set of core points and all of this sort of thing, I know how to do that, right? We all know, we all can, we all can download libraries to do this sort of thing. And that's what makes it possible to get those consistent solutions to getting these robust and faithful explanations. And just now to, skip now from the math to the actual, execution, here's an example image, and we vary the smoothness that's hidden over here. We vary smoothness over here, smoothness within the image, right? The image explanation should be smooth, and robustness across images along this axis. And you can see we can get all sorts of different explanations depending on, again, on what choice of parameters the human wanted, right? In terms of these two qualities. And what's really interesting also is that smoothgrad, which is supposed to smooth this way, claims to smooth this way, actually smooths this way, which is not quite what you would expect it to do. But anyway, it's kind of interesting. We also find that, in terms of this, for any finite n, the inductive setting is going to incur some loss. There's going to be approximation that goes on. But what we find, and this is with ImageNet, so it's a non-trivial data set, that as soon as as the core set of supporting points in the data set approaches or gets into the thousands, here's a transductive setting, here's the inductive setting, the loss in the inductive setting isn't that bad, right? So that it's not a crazy idea that, you know, the proofs are kind of like as n gets very large, but in practice, because of, you know, because we have good inference techniques, we can actually do this, you know, in practical settings. Okay. That said, you know, this is pretty early days in terms of this work. I think this mindset about like creating an optimization that's designed for a particular spec is a really cool way of thinking about explanations and the zoo of explanation methods that we have out there. And so I think there's lots of really interesting questions on how to create explanations that satisfy various types of specs, especially when there's these types of smoothness constraints and you're in this inductive set. All right. So I talked about this grand plan for generalizations, that tasks are going to get linked to properties, then explanations are going to be optimized for those properties. We talked a little bit about both of those things, but I don't want to leave out delivery, right? Because delivery also matters. So when it comes to, and let me just give you an example now, concrete example of delivery, right? So it's not just about the content. And like when I came into the field, like my PhD had nothing to do with people, really, like very little to do with people, right? Yeah, I was doing reinforcement, like I know it was applied. I was applying Bayesian nonparametrics to RL, right? So that was my notion of application. And I had this kind of viewpoint of like, you just, okay, we're working with people, you just give them information, they'll use it properly, which was quickly an idea that I was like, no, it's very much not true. So this is why there's interesting other problems though when it comes to human AI interaction. It's not just about presenting the right content, that was most of this talk, but also about delivering it in a way that people will actually use it in the most effective way. So here's a specific example. So we did a study with 200 psychiatrists, and we gave them two different types of, we created information about the patient. We created two different types of explanation for the recommendations. One was this very glanceable thing where you just look at some top features. And another one had a much longer description, like if you're concerned about QT prolongation, then favor sertraline, avoid citalopram. And it was like harder to read. And overall, if you looked at subjective scores on like helpfulness, people didn't like it. So this is the expert explanation, and they were like, that's annoying. Like having to deal with it, read these sentences is annoying. But they did better, they had much better performance with them. And the hypothesis is that the clinicians did not sufficiently engage when the explanations were too easy to process. You know, and they were like, oh, it looks about right. Whereas when they had to spend a little more cognitive effort reading the explanations, it made them unhappy. Because none of us want to do that additional cognitive labor, but they did a better job, right? So there's an interesting question there about like, how do you make sure that you get the right type of engagement? And one thing that we have to be important to be careful about is that we can't just be like, pay attention, right? Like that just does not work as a strategy. Like I'm sure you know this about yourself as well. You know, cognitive labor is a type of labor like any other type of labor, and we try to avoid doing labor, right? And so we want to be smart about asking for this. So these are the sorts of things now we did in a synthetic study. So the first study that I showed was with real psychiatrists, 200 real psychiatrists. This is a made up thing so we could run it with lay people on the internet. So there's a treatment plan that you have to decide, and there's some AI input and explanation. And what we tested was, should you give the information all at once, like I showed over here, or should this information come after someone's made a choice, and then you say, by the way, the AI thinks this, right? And what we noticed is that when you give the AI after, it usually increases the amount of time that's taken. But in some cases, it also increases the accuracy. And so maybe there's an opportunity here, and AI before reduces the amount of time. So maybe there's an opportunity here to say, I'm not going to ask you to use your brain all the time. That would be unfair, right? Like, what is the point of an AI decision support if I have to do more cognitive labor, right? But for the easy problems, maybe I can reduce your cognitive labor by saying this one's easy, it's routine, here's a choice. But for the hard questions, maybe I say, this is a hard question. I do need you to walk with me and engage with me on this particular question, right? And you're more likely to get it because you saved people time on the easy questions, right? So that was the first set of studies that we did in this space. This is based off of, is the questions easy or hard? Now, when we analyze the data, we also realize that people are different. No surprise there, right? And some people actually like to, are AI skeptics, or people that like to think, they like doing puzzles. Maybe the people in this room, right? And other people a bit more lazy, right? As soon as you give them the opportunity to turn their brain off, they will. And so when we look at the difference here, we actually see the different explanation delivery in terms of AI before and after benefits these different groups differently. So for the AI before people, you could give them information like in advance and they'll use it. If you have the over-reliers though, especially for the hard questions, you really don't want to give them the AI before, that's over here compared to over here, giving them the AI after, because they're just going to go with whatever the AI tells them. And that's fine if the question's easy, because then they do it fast. But it's not fine if the question is hard, because then they don't engage well enough. So this is also an interesting personalization question. And then being being a core, RL is like where I started. There's an opportunity here to personalize, right? As you start observing people, can you figure out, are they an AI skeptic or are they an AI believer? And depending on what sort of person you are, maybe we can tailor. And so these are the most recent set of results that we have that suggests, again, that the kind of idea here, which was like analysis that was done retrospectively, can be done prospectively, personalizing based off the data that you see about how the person's using the system. But one thing that was really interesting, and this caused a lot of angst in this particular submission, is that the results don't match exactly, right? These pictures don't look like these pictures. I'm not going to go into the specifics of which parts don't match, but they don't match exactly. The big difference was that in this study, the first study, people used a system for 10 minutes. Based off of that, we changed the system for the second half. And in this one, we were like, we're going to do it faster. So we will not require you to use a system for 10 whole minutes before we personalize. What would be the fun of that? We are going to try to personalize as quickly as possible. As soon as we know what type of person we think you are, we're going to switch you to the right intervention. And so we could often do this so this would be the 10-minute point. We could do this very early, just like at like 20% into the study, we could switch some people into their bucket. But what we found is that if you switch people early, they're a different person. Because if you've interacted with the system for 10 minutes, you started building some notion about how the system works, right? And you have come in with all these priors that inform the next 10 minutes of your engagement with the study. Whereas if you've only interacted with the system for, let's say, a minute or 2 minutes, you don't have that built background. And so when you do the next 18 minutes of the study with a personalized system, you actually interact with it very differently. And so this, leaves, last open question that I'll mention is that, it's not like you're just a over-relier or an under-relier, right? And that is your trait. And you are always a lazy person or you're always a really thoughtful person. The thing is, like, people change, right? And they change based off of the information that has been provided to them up to that point in time. And so from a back-end methodology question, I think there's a really interesting question of how to keep adapting the system to the user to meet them wherever they currently are. And again, this is obvious, right? But it's kind of interesting just how different those results were across these two settings. All right. As a last one last open direction that I'll leave is that these are fairly simple interventions, like before and after, right? Delivery interventions. But we've also thought about much more complex and interesting interaction mechanisms. We did a qualitative study where clinicians were given something that, rather than giving them recommendations, allowed them to first populate it based off of the patient's health record, some recommendations, but then you could go in and you could change things about the patient. And they loved it because they were like, oh, this is fantastic because I can adjust the information because maybe the patient never had a visit for insomnia, didn't have a diagnostic code for insomnia. It's not in their record, but they have trouble sleeping. And we'd like to put that in so that all of these recommendations kind of appropriately take that into account. So there's such a rich set of interaction mechanisms that are out there, and then trying to figure out how to provide the right information, how to make sure, how to optimize this interaction so the right choices get made at the end. Again, a really rich set of interesting problems that maybe LLMs will all solve, but I'm still not sure. You know, I doubt it. I think there's going to be some interesting back-end optimization to be done in these small data regimes. All right, so bringing this all to a conclusion in terms of toward effective explanations for this AI decision support setting. I started out the talk by saying this idea of properties may provide a key to generalization, because we can identify what properties are needed for what tasks, and then we can build explanations to match those required properties. And also in the second part, that there's a lot of interesting methods questions or human AI methods questions and how to personalize the delivery of the explanation. That just delivering the right content is not enough, or providing the right content is not enough. We have to present it in a way that people will appropriately engage. And that also creates like interesting machine learning questions to be solved. And you know, I guess I didn't realize the connection of like, okay, this is AI for science workshop, but you know, this idea of doing good science, I think, is especially relevant in the interpretable machine learning space. There's just a lot of papers out there, and there's a level of rigor that I really feel like we need to be able to move this field forward in terms of like how to think about questions precisely, and all of that. You know, I know a bunch of people in the room are like real scientists, like card-carrying scientists of various kinds. So I hope that there are opportunities to take that kind of rigor of you know, experiments and you know, experimental design, and bring some of that to the integral machine. Thank you very much. I'll take questions.
Whether you could say something about trust, where you see trust in the pipeline you define, because I could be a doctor who somehow, I don't, the explanation might be the greatest you can optimize on, but I choose not to trust because there is a lot of context to my choice that's difficult to control properly. Is it something that matters?
So can you expand a little bit? Do you mean trust in the like, do you want people to trust the system, or are you talking that the people might not trust the system due to some external factor, or?
I guess I mean both.
Okay, you mean both. Okay, so for trusting the system, I think an important part is just calibrating the trust. So if the explanation helps you figure out that the system should be trusted now, then that's good. But if it also points out a factor that makes you think, oh, I shouldn't trust the system right now because, you know, I've never seen it's giving me an output that this patient is so different from anything that this system has seen, the explanation doesn't make sense. That's also a win, right? Because then you don't use the system when you shouldn't use the system. I think there's a higher level, though, of trust maybe that you're referring to, which is just the overall trust in using the AI system, period. And there was actually really interesting. So when we did the qualitative study with that last interface, people really loved it. No one questioned the accuracy of any of the numbers or anything we're providing. And when we asked them, you know, because we were at the end of the interview, if they didn't bring up trust as an issue, we asked them like, well, what do you think about trust? And they said, well, why would the hospital system buy something that we couldn't trust, right? And to some point, it's a fair point, right? Like if you're a busy clinician, your point is to treat patients. You don't want to be thinking about whether the piece of software that the hospital has bought is a shoddy piece of software, right? So I think that there is some interesting work to be done to figure out how to, again, place these systems that are imperfect in settings where they can do good, but are going to require some level of engagement and critical.
Very interesting talk, Manali. I was wondering what your thoughts on shared decision making with patients were, and then, settings where the decision on, which therapy, will, be involved will involve trade-offs in the values of the patient. So, choice of surgery or not, or
100%, yeah.
cancer therapy.
That's right. So one thing that was really exciting about this study, which was just with clinicians, but actually we've just submitted a grant to expand this to include patients, is that the main outcome, actually, the main thing that got the clinicians excited about this is that they were like, oh, a simple interface like this, me and patient can sit together and you and I can click buttons and be like, actually, I care about this side effect. Can you remove everything that has the side effect? And so that it was not something that we initially had thought was like going to be a pro. Like initially we were thinking, oh, this interface will allow for correction, because like that's the data. But it turned out that they were really excited about how something like this could help filter and have a conversation with patients, and that's actually something where we just submitted a grant to expand this and figure out what patients really want. Yeah,
awesome.
It's very important. Yeah.
Sorry, about the loss functions that you were defining, like, does they interfere with the accuracy of model, like, or?
No, so all of this is assuming that the model is fixed.
Okay.
And we're just trying to explain the model. Now, if the model is like, to your point, the other question, if the model is inaccurate or is problematic somehow, then the best we can hope for is that the explanation exposes that the model is no good.
Okay, yeah. So you are fixing the model, and then it's a kind of post-processing thing that we try to improve the
That's right.
explanation.
Now, we've also done work, maybe this is what you're alluding to, where you try to optimize the model and the explanations at the same time. Because maybe if you want a certain smoothness in your explanation, there's going to be a smoothness fidelity trade-off if your model is like doing this, right? And maybe your model shouldn't be doing this anyway. It should be a smooth line because it's overfitting. And so absolutely, there's really interesting opportunities to also do joint optimization. And ultimately, I think most of the work that I've seen that do joint optimization get a lot of other benefits, because basically the interpretability penalty acts like a regularization against overfitting.
Yeah. The other question regarding that personality things that you said some people are lazy, some of them are less lazy. How do you assume what is the personality of the person, kind of?
I mean, you mean, why did we choose those two categories, or how do we figure
No,
it out?
I understand that those categories are existing, but I mean, the first point is
so
to,
we look
because
at
you said we have done for some of them, we give them first.
Right,
for
so
some
we
of
look,
them.
so specifically we look at over-reliance rate. So we can probe people, we can give them a bad answer and see if they go with the bad answer. It's kind of, and so these checks are like actually TSA, when you go through airport security, they put fake stuff into the images as a security people have to click to make sure that the people are not falling asleep, because it's a very boring job, right? Like all the bags going through. So similarly here, we put in various probe questions. We found that probe questions are more accurate than we tried other things, like how quickly do you respond? Like, are there other predictors of how engaged or not engaged you are? But ultimately, putting in a couple of these probes provided very accurate information very fast.
Yeah, super interesting talk. I'm curious about like thinking in the space of different properties we want from interpretability. So like the things you presented, like fidelity, smoothness, robustness, those are things that we can define mathematically, or at least have some sort of mathematical proxy of them. And I guess I'm curious, extending this framework then to other properties, like assuming that fidelity and smoothness and robustness are just scratching the surface of the different properties. To what degree do you think that we are going to be able to define these properties in similar mathematical ways, or is there going to be like a limitation where like we have to, like, new properties are going to emerge that, like, similarly to the reason we need interpretability or explainability in the first place, we're hitting the limits of what we can define?
Yeah, well, I mean, I think the property to task part is always going to require a bit of user study. So that's not it's not like, even if you could define the full list of properties, you're not going to get rid of the part that still needs the human involved. I think it's a really interesting question. Like, for example, another property that you might want that has something to do with compactness might be semantic alignment. That it's much easier for you to understand something if it matches the way you already think about the world. Whereas if I have to teach you an entirely new set of stuff, it's gonna be harder. And I think that's a good example of something that I think probably can be formalized, because you could talk about, whether various embeddings match and embeddings or stuff like this. But it's much more difficult to formalize. So I think it's a really interesting question about just how far we can push those boundaries. I think we definitely have room to mathematize more than we have so far. And the way I also see this is that like human time is really valuable, right? Whether it's a worker on Prolific or Turk, or whether it's like an expert, domain expert. And I see like my role is not wasting people's time. So the more that can be done in silico computationally to avoid presenting a clearly bad version, I think of that as like, okay, this is a win. So even if we get 80% of the way, I still think that's some benefit.
There's a question from the audience online, which is, in personalization, do you see a value or need to empower users and give them more choice about the interventions they're going to receive? So maybe going all the way in, presenting explanations on the interventions as well.
You mean like because we think that you're lazy, we're making you do some homework first? We've actually thought about this, not quite in those words, of course. But what would the effect be if you told people that this is roughly the type of user that he seems to be in, or because it could go badly, but it could also go well. Like if you tell people that, hey, it's easy to check out, and we want to make sure that the baggage safety is maintained, or it's an semi-autonomous car, but you need to be having some situational awareness. I think people can get that. So I think that there is a world where appropriately presented, you can actually get better behavior out of people if you tell them that, hey, we realize we're all human, we're all imperfect, and we're trying to help you through the flaw, our imperfections. Yeah.
One question: do you apply this framework when you submit grants to better your possibility of getting grant money?
What, you mean explanations?
Yeah.
I don't. Tell me the secret. I don't quite see it.
No, I mean, like, you can predict the outcomes of how people interact, or like, but like, can you make the explanation tailored for like reviewers?
Oh, I see. I see. I wish. It's a work in progress. Yes.
Do you know if the users are like rating themselves? Like, I'm really sleepy today, I need the AI to help me more.
That's a good question. We have not tried that. We've asked users questions like, do you enjoy doing puzzles? Do you need to, when information is presented to you, do you prefer getting a detailed explanation as of why, or do you just trust, in those sorts of things? And those definitely correlate to some of the traits. Or it's not really traits, it's like the quality in the moment, right? Like maybe right now you ask me if I'm interested in puzzles, I'll say yes. If you ask me at 11 p.m., I'll say no. But I think it's a really good question about like how self-aware people are.
Maybe I'll ask one more question, which is, is personalization a good idea? So just to play devil's advocate here,
Okay.
If you have the goal of convincing someone that the thing you've done is interesting, then, personalization might take that to hide or obfuscate aspects that are crucial to understand for the domain expert to give you like really critical feedback. And in some sense, there's a trade-off. There's like a goal that you have, and there's a goal the domain expert has, and there's some reality of the system that you're building. And that's maybe my, question around this. Like, how do you think about those three competing interests?
Yeah, I think it's a really interesting question. So we are focused in situations where interests are aligned, and where manipulation is not the goal, right? If manipulation is the goal, then clearly the more you can personalize, the more you can manipulate. We've seen that with various things on social media. So here, really the assumption is that both the patient, the patient, the provider, the health system, all want, you know, a certain type of like good, positive outcome for the patient. If that is not true, then absolutely you run into a lot of issues, because then the more you optimize, whether the optimizing the content or the delivery or personalizing to the person, the more opportunities you have to manipulate someone to do something that maybe they didn't want to do, but the system wants them to do.